Teams run polls, see a small lead, and then launch the wrong product because they thought that lead was real. The mistake is believing that a small sample is either worthless or must match the population in every visible category to be trusted. Mathematically, that confusion swaps random error, which cancels with proper design, for systematic error, which does not cancel and pushes estimates in a consistent direction. Picture yourself watching early survey results trickle in. The curve looks steady, and before you notice it, your sampling choices have quietly locked in a skew you cannot see. Start with the objects on the table. The population is the entire group you care about. The parameter is a fixed but unknown summary of that population, like the true average or the true proportion. The sample is the subset you actually measure, and a statistic is the summary you compute from it. We use the statistic to infer the parameter, and everything that follows is about how trustworthy that leap is. Take something concrete. You want to estimate the typical commute time in a city with roughly 2 million residents. You cannot ask everyone. You do not need to. If you select a small group in a way that gives every resident a known and fair chance to be picked, the average of that group is a reliable pointer toward the citywide average. The reason this works is simple and not mystical. Random sampling lets the small errors in opposite directions cancel out because you did not stack the deck toward any specific subgroup. If the fast commuters and the slow commuters are both just as likely to land in your list, their contributions push the sample statistic around in a balanced way. The expected push is centered on the true value you are trying to learn. Now contrast that with grabbing whoever is easiest to reach. If you post a link on your own social feed or ask only the people who pass your office, you have built a convenience sample. The pattern of who responds is no longer neutral with respect to the quantity you care about. You get a clean-looking average that is cleanly pointed at the wrong target. Randomness is not a vibe, it is a mechanism. You need a clear rule that does not peek at who someone is before deciding their inclusion. Use a random generator to pick people from a complete list, or draw times and take whoever shows up at those times, or use a map and select addresses by chance. Independence matters too. If you take one household and then take 3 of their close friends, you have not added 3 independent voices. You have copied the same influence. Here is the common beginner mistake. They think representativeness means the sample must look demographically balanced by manual tweaking, so they chase quotas or eyeball splits. Or they think size alone is salvation, so they blast a giant but skewed audience and call it a day. Both choices leak the thing you actually need, which is a credible story about how each member of the population had a fair chance of selection. This costs you in very tangible ways. If your sample process leans toward heavy users, you will overestimate satisfaction and underdiagnose friction. If it leans toward people who answer during work hours, you will misread the habits of people who are unreachable then. The damage is not just noise. It is a directional tilt that does not fade with more data from the same flawed pipe. Here's the correct mental model for size and reliability. Random sampling creates wobble around the truth, and averaging across more observations reduces that wobble. But the reduction is not linear. Each extra handful of responses helps less than the previous handful. The gains from going from small to moderate are dramatic. The gains from going from large to gigantic are modest. Your goal is enough, not endless. Put a number to the story so you can feel it. Imagine the true average commute is 30 minutes. A well-executed random sample will give you a sample average that hovers around that value. Sometimes a bit high, sometimes a bit low. As you increase the size of that sample, the typical miss shrinks in a predictable way. You control the process, not the exact outcome, and that is enough for rational decisions. Independence does more work than people realize. If your picks cluster in a few neighborhoods or around a single workplace or inside a single social circle, then your effective amount of information is much smaller than the headcount suggests. You can create independence by spreading your selection across times, places, and frames, and by resisting the urge to accept substitutes that are easy but similar. The aim is not diversity as a slogan. It is independence as a mathematical requirement for cancellation to happen. You have seen a poll that says the margin of error is about 3 percentage points. That number is not magic. It comes from the typical spread of a proportion when the sample was selected at random and the responses behave like many independent yes or no outcomes. The tighter that spread, the less room there is for random swings to mislead you. The wider it is, the more humility you need in interpreting differences. There are refinements that keep the random logic while using structure in the population to your advantage. Stratified sampling means you partition the population into meaningful slices, like regions or age ranges, and randomly sample inside each slice. You do this when you know the slices differ on the outcome, and you want to ensure each slice is represented in proportion to its size. You still use randomness inside slices. You're not handpicking winners. You can also accidentally increase noise without realizing it. Cluster sampling, like picking a few schools and surveying every student inside, is cheaper but comes with correlation inside clusters, which inflates your variability. If you use clusters, you have to account for that inflation when you summarize uncertainty, or you will sound more certain than your design justifies. Cheap and fast is fine, but not if it hides the true wobble. Here is a practical checklist to keep small samples honest. Define your population in operational terms so you know exactly who qualifies and who does not. Build or obtain a sampling frame that lines up with that definition and note any gaps. Generate selections using a legitimate random device and record the method. Protect independence by avoiding chains of referrals, time slots that favor specific groups, or repeated pulls from the same pool when that creates correlation. Pre-commit your sample size and stop rule so you do not shop for a lucky run. Do not treat a sample statistic as the truth. Treat it as the center of a distribution of plausible values. Report the estimate with an expression of uncertainty that follows from your design, and link the size of that uncertainty to both the natural spread of the thing you measured and the number of independent draws you made. If those two inputs are large and small respectively, your uncertainty will be wide. If they tilt the other way, it will be narrow. This is not decoration. It is the whole point of inference. Connect this to the longer path you're on. Randomness and independence give you a sampling distribution for your statistic, which is the mathematical object you will use for confidence intervals and testing. The logic that makes a small group speak for a population is the same logic that makes those later tools work. When they fail, it is almost always because the sampling step was careless, not because the math of averages stopped working. The shift you need to make is this. Representativeness is a property of the selection process, not the final roster. A small, randomly selected, independent sample can speak reliably for a vast population because its errors cancel on average, and the remaining wobble can be described. A big, biased, dependent sample cannot be rescued by sheer size or by pretty demographics. Once that is clear, you will stop arguing about how many and start insisting on how they were chosen. Next, we tackle sampling bias, how bad data collection destroys valid conclusions because all the math you just learned collapses the moment the selection step leans in a hidden direction.